welcome to this classical statistic pitfalls and remedies lesson for the QLS 612 class. My name is Jean-Baptiste Pauline, and we'll be going through that theme. First, a quick overview of the lesson. I'll talk about the p-value and the null hypothesis testing framework and the misinterpretation of this framework, the p-hacking issue, the file drawer effect, the winner's curse, the effect sizes, and then power, and then positive predictive value, and last statistical generalizability aspect. So let's get started with the p-value and the null hypothesis statistical testing framework. First of all, a quick reminder: while the reproducibility of, let's say, on the same data for the same pipeline is really mostly a computer science issue or scientific field methodology issue, really what replicability and generalizability they are really statistical issues. So that's why it is important that you take that lesson. So p-value to address the solidity of a result. As you may know already, the p-value number is very dominant as a tool to state whether a result should be trusted or not, a scientific finding should be trusted or not. They are simple to compute, and every statistical software will implement p-value or statistical testing, and therefore p-value. P-value originally were developed by Fisher in the 1920s, and the null hypothesis statistical significant test, the framework was developed by Neyman and Pearson to more to make a decision rather than to indicate the strength of an effect. So let's first of all review the null hypothesis testing framework. That framework is simply stating if you have an effect, you just assume that there is no effect. Let's say you want to test for an effect, you assume that there's no effect. You construct a null hypothesis, and the way you control the risk of error is just by stating that you don't want to say too many times that this null hypothesis is rejected, and therefore that you have an effect in your data, while this is not true. So, so the control of the type 1 error is the thing that is really driving the null hypothesis testing framework. So again, when the null hypothesis is true, you don't want to reject that hypothesis too many times, and therefore you put a threshold of how many times you want to reject that null hypothesis. So let's see how people understand that framework. And to do this, I've taken this old example of a test given to medical students. And the test was the following. Consider a typical medical research study, for example, designed to test the efficiency of a drug, in which a null hypothesis, H0, no effect, is tested against the alternative hypothesis, which is there is some effect. Suppose that study's result pass a test of statistical significance, that is a p-value of less than 0.05, in favor of the alternative hypothesis. What has been shown? And the question is, have you shown that H0, the null hypothesis, is false, or the alternative hypothesis is true, or that H0 is probably false and H1 is probably true, or both 1 and 2, or both 3 and 4, or none of the above? And if you take 15 seconds to try to answer this, I mean, my experience is that many of you, at least, will answer something probably 3 or 6, or H0 3 or 4, or 6 3 and 4. Something like H0 is probably false and H1 is probably true, or both that. So that's the usual. I would think the majority of the answer are often in that response. The true answer is actually none of the above. And as you see, the medical students don't actually answer the true answer either. I think, and many researchers will actually be also tricked by that little test. And the reason is that of the definition of a p-value is that the p-value is the probability of observing a statistic equal or more extreme to the one seen in the data when the null hypothesis is true. So the thing is, it doesn't tell you something on the hypotheses themselves, or either the null or the alternative. It tells you about something about the data. So it's really about the statistic of the data and how that statistic of the data behaves, if you want, under the null. So first of all, what is a statistic? Well, it's any function of the data. So take the data, compute the mean, that's a statistic. Compute the standard deviation, that's another statistic. The t statistic, the z statistic, all those things are just function of the data. So under the null hypothesis, you have to know what is the null hypothesis. So that's a very strong thing to know. Like you have to decide this is my null, and I'm going to reject when my statistics is above a certain value in that null distribution. So you have to choose a statistic, and you have to have the concept of repeating the whole study in the same way an infinite number of times. That concept of frequency, the probability as a frequency as well. So it's not a natural sort of a framework where you're saying, okay, I want to test the alternative hypothesis. You're always testing the null, and then you're rejecting the null to find out something of the alternative. An interesting quote from Neyman and Pearson in 1933, which already said at the time that we're inclined to think that as far as particular hypothesis is concerned, no test based on the theory of probability can by itself provide any valuable evidence of the truth or falsehood of an hypothesis. So it's a very interesting quote given the usual perception of what is the null hypothesis testing framework. So let's take a couple of examples of a null hypothesis. The most common one is, of course, the normal distribution centered on 0. That's an important aspect. The null will be most of the time centered on 0. It doesn't have to be. Doesn't have to be. And if you look, for instance, at a statistic that is above 1, so 1 or more extreme, the p-value would be 0.159. So something, let's say 16%. So it would be rejected at a 16% error rate if you want. But if you wanted to look at something like a statistic below or equal or below minus 1.96, that would be 5% divided by 2, 0.025. For the same values of the p, a gamma distributed statistic would have extremely different x's or statistics. So for instance, 0.05 for x here and 3.6 or 3.7 for the p-value of 0.159. So different distributions for the null, obviously different statistics for the same p-value. An interesting and important fact is that p-values under the null hypothesis are uniformly distributed, and this is just a random sampling of the p-value under the null here, and you see how they are uniformly distributed across between 0 and 1. So that's and the reason is that when you want to reject the null, you want the probability of rejecting the null to be alpha. So the probability of observing a statistic greater than that alpha quantile is alpha. So for instance, if you take probability that the p-value is smaller than 5%, that is the probability that the observed statistic is above 95% percentile of the null. So is 5%. So the probability of p being less than 5% will be 5%. And that is the kind of the definition of the uniform distribution. Again, it reminds us also that a p-value is a statistic itself. It's a function of the data. You take the data and then you have a way of computing the p-value with those data, and therefore the p-value is a random statistic, random variable, and it is if your data are random, have some randomness, and therefore it is a random variable. The fact that the p-value is uniformly distributed is also used in the p-hacking test that I will describe later. So what are the common problems associated with the p-value interpretation? The most common misleading interpretation is that to consider the p-value as the probability of the null hypothesis, that the probability of the null hypothesis is true. So if it is not, because it is a probability of observing this data under the null, or something more extreme if the null is true. If trials are conducted with a control type 1 error, say 5% type 1 error in a trial, and with adequate power, let's say 80%, I'll talk a bit more power, so bear with me with this, but let's say a good probability of detecting the alternative hypothesis, of rejecting the null when the alternative is true. Then significant results almost always are corresponding to a true difference between the treatments compared. So that is wrong as well, and that's something that is also a bit tricky, and so read that carefully. And the reason why it is wrong is that those, let's take an example. Let's take that we have like 1,000 null hypotheses. For instance, we are testing 1,000 brain regions or 1,000 SNPs on the genome, and so we're generating 1,000 null hypotheses. And let's say that 10% of those null hypotheses are actually false. So therefore, there's in 10% of those brain regions, for instance, there is some signal. There's a non-zero effect. Then there is 900 true null hypotheses, of course, and within those 900, with an alpha of 5%, we are going to have a 45 false positive, right? And we're going to have like 855 non-significant results. For the 10% of the 1,000, so the 100 false null hypotheses where there is some signal, with a power of 80% or type 2 error of 20%, then the significant results will be 80 detection. So the true positive will be 80 detection out of those 100, because we have 80% power on average. And the false and the non-significant result will be like 20. So if you look at all the significant results, they are made of 45 of significant results due to false detection in the null, right? And false detection, and then 80 for like actually true detection. So the ratio of 80 out of 45 plus 80, so 125, is 64%. So 2/3 of significant results are true positive. So 2/3 are true positive with a 5% type 1 error and with like 80% power. This is actually what is also called in some other context the positive predictive value, and we'll see that statistic later on. So a few misconceptions and a few kind of a take-home message for the p-value. P-values can indicate how incompatible the data are with a specified statistical model. That's what the p-value are. P-value do not measure the probability that the studied hypothesis is true, or the probability that the data were produced by random chance alone. That's not what they do. They don't talk about the hypothesis, they talk about the data. Scientific conclusion and business policies should not be based on only on whether a p-value passes a statistical threshold. So like a p-value by themselves are not sufficient to make a decision. Proper inference require full reporting and transparency. So that's really important, that you can't report some of the p-values and not the others. If you do multiple testing, for instance, that those sort of that would very much bias the results. A p-value or statistical significance does not measure the size of an effect or the importance of a result. It could be that somebody do. And by itself, a p-value does not provide a good measure of evidence regarding a model or hypothesis. So just have those caution elements in mind when you're using p-values. Let's go over the p-hacking issue. And I think I've talked a bit in the in my lesson on the reproducibility basics. But just to remind you, what is p-hacking? P-hacking, first of all, has a long history, but the best paper to describe it is probably the Simons and Simonson's 2011 paper, where Simon and Simonson's studied how we could come up with a much bigger type 1 error than we usually do, than when we think. And the way we come up, we have like much bigger type 1 errors is basically because we're often doing many statistical models or many trials and errors on the same data. So after having done all those trials of different inclusion or not of covariables or removing some outliers and so on, the type 1 error is actually much higher than the one that we specify with a 5% if we do many of those tests. So most often this is not intentional and can be also difficult to detect even for the researchers themselves. As soon as you've seen some data, you already can be biased in your hypothesis testing, and that is important to note. I mean, the most obvious way is, let's say you look at the data, you find, oh, this group seems higher, I'm going to test that group against that group values. That's an obvious way, and most people are aware of that, but there are more subtle ways of being of increasing your type 1 error risk. There's a p-hacking test that is based on the property of the p-value to be uniform that I was describing before. The p-value test is looking at a body of literature and seeing what is the distribution of the p-values in that body of literature. And if that distribution is flat, then you're probably under the null. If that distribution there are more small p-values than p-values close to 0.05, then there's probably some signal in the literature, in the results. But if there are more p-values closer to 0.05 than p-values that are smaller, let's say 0.001 or 0.001 and so on, then that means that the curve is actually on the opposite, has a different slope than it should have. Like if it's random, it should be flat. If it's the signal, it should be going up. If it's going down like that with more p-values at 0.05 and less with smaller p-values, then there's probably some p-hacking. And so the authors have designed, the Simonson et al. 2014 paper designed a test for detecting those situations in the literature. And there's a couple of references that you may want to look at, and we will probably go in our in vivo session, exercise session, with some exercise on p-values and p-hacking. So what are the solutions? The best one is definitely the pre-registration. If the study is in that setting. There's been a number of solutions proposed in the literature, in the blogosphere and the literature and on Twitter, and some of them are quite extreme. Like there was a proposed ban of the p-values by a psychological journal. There's the change of alpha. So let's say we know that we are not correct when we don't have like a good evidence with 0.05 because of p-hacking or because of just 0.05 is not strong enough for good evidence. Let's change alpha and always use, let's say, 0.001, for instance. And I think that's the key aspect here. Complement with other statistics. Make sure that you're not reporting only the p-value. Let's make sure you report everything, and let's make sure that all the aspects of your data are described, and the way you have analyzed the data is described in details. I'm going to quickly remind you of what is the file-draw effect. It is an important effect in the literature. And the file-draw problem is not new. It's been described by Rosenthal in 1979. And basically, the file-draw is the idea that if you have a paper that if you find something that is passing a statistical threshold of, let's say, 0.05, for instance, for a new finding, that article, that finding is likely to be reported in the literature. But if you don't have a finding to pass a statistical threshold of 0.05, that finding may not be reported in the literature. It is likely not to be reported in the literature. So that's the problem. And therefore, in the literature, you get many more, you get only the filtered findings that are surviving the 0.05, and therefore you don't see the null results, which would balance the literature, the results. Let's say 100 labs does an experiment, only 5% of those 100 labs find an effect, and then only those 5% will be will be published in the literature, and you'll have like something that looks solid because it's been replicated by a few labs of the same results. But in fact, if many more labs have tried and not found anything and not published that null results, then you have a very biased results in the literature. And indeed, if you look at the z-value in Medline, and you look at the distribution of those z-value, you find that there's a huge gap of all the z-values between -2 and 2, because most of the papers won't report anything that is between -2 and 2, because it's not corresponding with the Gaussian as the null hypothesis. It's not going to be a significant result. So you find a lot of results of z-value that are close to 2, and then or -2, but not in that area. So that's a very interesting. I mean, keep in mind that if you see results in the literature, there might be other results that have not been published and are not results. So what are the remedies? What can we do to avoid that problem? I think one of the key things is the pre-registration. And if you can, you should pre-register, make sure that you record everything that you will do in terms of analysis of the data before you analyze the data, before you see the data. And then we collectively can try more a cultural shift where we can try to convince editors and journals that the null results need to be published. And one aspect which is really important is that convincing editors that null results need to be published is important. It only can happen, it really will happen if we can make sure that there is sufficient power in the study. Because if you have a null result but very little power, that result is almost predicted, right? It's you have very little chance to detect anything anyways, and therefore if you don't detect anything, nothing is surprising there. You're not adding information to the body of literature. If you have a lot of power to detect a small effect and you don't find it, then that is information that is very valuable to report, and hopefully editors and reviewers will agree with that. And then, of course, the null hypothesis testing framework is not the only statistical framework. There are you can put your study in a more like a predictive framework, and I will refer to the machine learning modules that you may follow for this with this course. Or you can find yourself put yourself in the Bayesian framework and try to report evidence such as Bayes factors, for instance. I'm going to quickly now describe the winner's curse. What is the winner's curse and when does it occur? So the winner's curse is when associations passing predetermined thresholds of a statistical significance tend to overestimate the size of the effect. And I know we haven't looked at what is the effect size, and we'll see, but bear with me. Effect size, as we know it, is the measure of how what is the effect that we see. So this winner's curse is showing you, is telling you that when you have a predefined threshold, when you have this thresholding filter, and you have small sample size, and possibly a stringent type 1 error, so 5% is not very stringent, but it's stringent enough that the effect will occur. Then you will report overestimated effect sizes. And I think this is seen in many areas of science and not always very well understood. So we are talking about effect size. I just want to go over effect sizes a little bit more in depth because it's not always clear what is an effect size, although everyone has an idea of what is an effect size. It's not always entirely clear how we can compute those things and what they are. I'll take the very simple example of the difference between two means. So you got two groups, mean 1 x1 and mean 2 x2. And the difference between those two means in an instance where we want to see whether there is a difference between two groups for that specific measurement is clearly the R effect size here. But that's a raw effect size. The standardized effect size is the one, or the QLSC effect size, is the one that is corrected or normalized by the standard deviation of the data. So have a measure of the standard deviation of the data and then normalize that effect size, raw effect size, by the standard deviation of the data. So mu over sigma here. And then if you were to additionally correct for the sample size of the study, then you probably end up with something close to a z-value. So in this sense, for instance, here, the effect size divided by the standard deviation of the means, or the standard deviation of this effect size, so like the difference of the means, and that will include the number of subjects, the number of sample in the study, and therefore that effect is depending on the size of the cohort. The standardized effect size, the QLSC effect size, doesn't. So three flavor of effect sizes for the same study, which I think is important to appreciate. It's a vague notion. Effect size is a vague notion. But what is a good effect size? I think it has to be simple. It has to be very interpretable. For instance, with units, units that make sense in the field. And it should be really as much as possible a standard in your field. If you have a standard reporting of something, then that should be is often an effect size. So, for instance, a correlation, difference the mean between the groups, but also the percentage of variance explained by an effect, and so on. And what should be reported? Basically everything, as much as you can, and as much as the journal will allow you. Guidelines for reporting in that are really important. It's hard to change the reviewers or the editors' mindset often, but nowadays almost every journal require have some basic guidelines for reporting, and I would really recommend that you report both the effect sizes, normalized and non-normalized, standard deviation of the means, confidence or credible intervals, And if possible, when that's not too costly computationally, I would recommend that you bootstrap your data and then redo the test such that you have a bit of an idea of the distribution of the result. So anything that gives an estimation of the uncertainty of the results is an important measure to report. I'd like to take a quick example. This is a famous study, an old one, a very old one now, showing the association between the activity of a brain region called the amygdala when it is lighting up when you, in general, when you see fearful faces compared to other non-fearful faces. So, and so the amygdala is responding to the fearful faces, if you want, and that effect seems to be higher for some carrier of a specific allele of the serotonin transporter gene. So that study was important and interesting, very interesting, and actually used a small group of 14 subjects, but was replicated on another group of 14 subjects. Twice the study showed the same effects on two groups of 14 subjects. So the authors report that the activity in the amygdala was 0.28 for the carrier of the long allele of the DNF gene, and 0.03 for the other group. And with some standard deviation of those means, and therefore reports the standard deviation of those means. So how do you compute the effect size from there? Well, you have already the raw effect size, which is 0.23 minus 0.03, that's fine. But if you want to compute the Cohen's d effect size normalized by the standard deviation of the data, then you have to work a bit. So how do you go from the standard deviation of the means to the standard deviation of the data? Well, you know that basically there's a factor of square root of n minus 1 involved. So you can go back to the standard deviation of the group, of the two groups. So sigma equals square root of 13 times the standard deviation of the mean of that group. So that's what you can do. And then when you have those two values for the two groups, then you can combine those things into an estimation of the standard deviation of the data. And then when you have that, you can compute the Cohen's d effect size from there. So that's one way of computing the effect size of that study. And the results show that the Cohen's d effect size is 1.05, which is a very strong, very, very strong effect size. Another effect size is the percentage of variance explained. And the way it can be computed is not very difficult, but I won't go over in this lecture. But let's just assume that you know how to do it. And actually, I've just putting up the formula, and we can derive that in the live session together. And that specifically that result was showing like more than 40% of the variance explained by this allele for the activity of the broad response, which is probably bizarrely high. So those values were not reported in the original publication, but would have probably raised some questions by reviewers because that's a very, very large amount of variance explained by this effect. Effect size, I'm just going on this the theme. I just want to remind you of the probably a winner's curse aspect in this study of the Brian Nosek study, showing that most of the effect sizes that are of the replication study, so on the x-axis again the original effect size, on the y-axis the replication effect size, and the green ones are the ones that are found again significant, if you want, and those ones are the ones that are not found significant. So showing that here only 40% of the effect sizes were found significant again, if you want, in that study. With the power is indicated by the size of of the dots here. An interesting follow-up study that I recommend by Murray and Larkins, showing that in fact the variation of the difference of the two effect sizes is very strong. So if you look here on the y-axis, you've got the difference between the original minus the replication effect size, and you see that most of those effect size, those differences are positive. So the original was bigger. So showing again the Wiener curve effect likely. But also showing the variation, the variability of those differences, and that was that variability is very strong. Basically, you may not be able to say anything but that difference because of that variability, and that's what the authors consider as and can be rejected. I mean, you can't. It doesn't actually give you some information. Right. So the next section is about the power computations and concepts, the concept of power. So just as a reminder, I think most of you know this, but I think it is important to make sure that this is well understood. Power is 1 minus the type 2 error, which is the risk of not rejecting the hypothesis when H1 is true. So basically not being able to detect the effect. So power is 1 minus that risk. So the higher power, the more likely you're going to detect an effect. So in this classical example or small example, I'm showing the blue curve as the null hypothesis as the blue curve here. So null hypothesis is centered on 0. And here on green is the H1 distribution, the distribution of the effect of under the alternative hypothesis. In red is the alpha type 1 error being chosen, so 5% in this instance. So power is really the gray area that is on the right of this vertical line here. So as soon as you have an effect that is above 1.96 here, almost 2, if that effect is above, then you'll be able to detect because you are above that threshold. And so the number of effects or the effects that are in that, the probability of that effect to be on the right side of that vertical line is the area under that curve here. So the higher the probability, of course, the higher the power. So what's going to drive the power? Well, first of all, the effect size. If you have your green distribution shifted on the right, then you've got higher power. You're going to have a bigger gray surface. The smaller the variance, and therefore, like if the variance is computed using the because the variance is computed with this number of sample aspect, then the greater the number of subjects, the smaller the variance of the effect, and therefore the greater power. And obviously if you change those distribution, you would change the power as well. So that depends really on the distribution of the effect. So all those things will affect power, and all those things we actually mostly don't know. So so why is it important still to compute power as much as you can? Well, because without good power, the study itself is probably not worth doing. And without a good power, the study results are doubtful. And that's what we will see with the positive predictive value. Power is really hard to compute. It's in general, I mean, like there are simple cases where it is simple to compute, but in general, you have to know H0, you have to know H1, you have to know the statistical threshold, of course. So a statistical threshold, that's kind of easy. Let's say you by default take 5%, but knowing the distribution of the effect under the alternative is a guess, and actually knowing the exact H1 is to some extent is a guess as well, or is a model that we are choosing that model, but we don't know whether that's actually a true model. So despite all those difficulties, it is worth estimating power when you can, because it will give you some at least some ideas of whether that study is worth doing. And as a reminder, low power and high effect size. So that's a classical issue. That if you have like a small sample size indicated by the size here of the circle for a specific association, here the BDNF and the hippocampal volume association, then a small sample size may lead to high effect size. Here the Cohen's d on the y-axis, and large sample size may lead to small effect sizes. And therefore, good power, but small effect sizes, so you might not still find an effect. And in our neuroimaging world, this is showing that again that in 2015-16 we usually had around 25 subjects per study in fMRI, and that lead to at 80% power to a detection that is possible at about with an effect size, or Cohen's d effect size of 1. And what is shown is in this Podrak paper is that the effect size found in the HCP, for instance, are probably around like a 0.3, 0.5, 0.6, 0.7 only in very, very strong places like the SMA, for instance, with the motor cortex or the motor cortex. Those are very, very strong responses of primary cortices. So with an effect size of 0.5, we have a power of about 30% with this number of subjects. So that doesn't give us much power for computing, for detection, especially if there are many regions to be tested. The almost last topic is the positive predictive value. So I wanted really to give you a bit of a precise idea of what the positive predictive value is in different contexts and why it is important to know about it. So first of all, I would say it's important to know about it because that seminal paper from John Ioannidis telling us that, explaining why possibly the most published research findings are false, is based on the positive predictive value. And the positive predictive value is the probability that the alternative hypothesis is true, knowing that the test is significant. So you find a significant test, and then you're asking yourself, knowing that I have a significant test at, let's say, a 5% error rate, is my alternative hypothesis true? So it's a bit of a change of paradigm because the hypothesis here is not either true or false. There's a probability associated with it. So it's not we are under H1 or we are under H0. It's an object that we are looking at the probability of that object to be true or false. So it's a change of a mindset a little bit compared to the frequentist aspect. So I just want to remind you that probability concept is not an easy one. It has many definitions and many settings, many framework. One of them is I've listed 4 probability frameworks as the epistemologist would tell you. And the objective physical properties, the subjective as a degree of belief, the frequentist probability, which is the most used and classical, in the classical framework, which is the limit of the frequency across an infinite number of trials. So let's say you throw dice, then you're looking at the probability of getting one from the dice, and that probability is 1/6 if your dice is fair. Because if you were to throw that dice like in a random way an infinite number of times, that frequency will converge to 1/6. So that's the frequent list aspect. But there's also the Bayesian probability, which is defined as a reasonable expectation representing a state of knowledge. And often part of that definition of a probability, as a definition, the Bayesian would say that the probability of two events co-occurring is the probability of, so A and B, is the probability of A times the probability of B knowing that A has occurred, so times the probability of B given A. And that's part of the definition most often of a probability in the Bayesian framework. And then from there, you can derive the Bayesian, the Bayes theorem, which is very simple once you have that. So here, in this instance, the probability of H, let's say, hypothesis being true, given some data, is the probability of the data and the hypothesis normalized by the probability of the data, which can be written using that formula below, above. The probability of the data knowing the hypothesis times the probability of the hypothesis divided normalized by the probability of the data. And to give you a bit more of a sense of what is the Bayesian probability, or is the Bayesian theorem. Let's say I receive a lot of spam and receive a lot of emails with free lunch in the body of the mail or in the subject, and the probability of a mail being a spam, knowing that it is labeled as free lunch, is the area that is both, representing the emails that are both spam and free lunch, normalized by the number of emails that are free lunch. So this is what the probability of A knowing B how it is computed. So let's go back to positive predictive value. Why is the PPV important? So because it measures the probability of the alternative hypothesis to be true, knowing that the test is significant, it is not worth concluding anything if that number is very small in general. So even if my test is significant, if I know that the probability of H alternative is being true, given that that test significant is, let's say, 1%, what does it mean to have a significant test? It doesn't mean anything. That's not very helpful. So that PPV is very hard to compute as well. It depends on the prior probabilities of the H1 or H0, the alternative and the null. Or their ratio, or the ratio of those probabilities. It depends on the power of the study, and it depends on the risk of error, the type 1 error, alpha. So let's not go to how we derive that. I just wanted to show you that with very simple statistical statements, we can derive easily the probability, the PPV, that probability of H1, H alternative being true, knowing the test is significant. And that's a very simple replace thing. So there will be no question on that. It's just like to show that it is a simple computation that you can do, and that the result is simple as well. It's if you define the ratio, the odd ratio as the probability of H1 divided by the prior probability of H1 divided by the prior probability of H0, then the PPV is W times this ratio, the power times the ratio, divided by the power times this ratio plus the type 1 error. So again, as the ratio is that the odd ratio is this probability of H1, H alternative divided by probability of H0. And that gives us a bit of a sense of how likely is H alternative compared to H0. Are we in a setting where it's almost as likely, or it's much less likely, and so on. So taking something that is in the middle range, or it's not very unlikely, but not very likely either. The PPV as a function of power shows that if you have a low power, even like with alpha equal 0.05 here, and an odd ratio here of 0.2, with a low power, you have like a low positive predictive value. So the probability of alternative being true, the alternative hypothesis being true is low. And if there is some p-hacking, if there's some problems in multiple comparison that are not well corrected and all those things, and let's say you have like instead of 5% risk of error, you have 30% risk of error, which is not a crazy number, unfortunately. Then that's a PPV goes down very quickly. Let's say with even with a power of 80%, you have one chance over 3 that your alternative hypothesis is true. Only one chance over 3, knowing that your test is significant. And if you have like both small power and large type 1 error, then that depending on the odd ratio, but even with large odd ratio, you've got very low PPV as well. So those things are well described in the Button et al. Paper, and showing that most of the neuroscience studies have a low power, and showing the effect of low power on positive predictive value and on the bias for the effect sizes. I just want to point you to the fact that in a machine learning framework, PPV is also called precision. And if you don't make those things probabilities, but if you just like measure results of a test on a specific data, then you can actually go from the PPV to what is called precision in machine learning very easily by looking at the number of true positive divided by the number of positive, so true positive plus false positive, and that is very easily related to the PPV in the more probabilistic setting. And there are other interesting numbers if you are in that setting of a specific test, or where you have let's say classifiers or statistical test over many occurrences. So PPV is one of them. The negative predictive value is another one, and then you've got the classical sensitivity and specificity numbers. And I like that figure because it makes it clear how you compute those things easily. Summary: it's hard to estimate well the positive predictive value. We need power, we need prior odds, so the probability of H1 divided by probability of H0, and we need a type 1 error. That type 1 error is the easiest of those three. So at least power and prior odds are usually unknown, but they can be estimated. It's interesting to plug in some numbers with some estimation of what you think, and to see what is the PPV of the study. And PPV in general may be quite small in studies. The last point I want to make is the statistical generalizability aspect. And the problem is the following. Is that the way we model effects maybe there are basically two simple ways of thinking of modeling an effect. One is either it has a new source of variance or error associated with it or not. And so we usually consider as fixed effects things that just depend on one source of error, of variance of error, and as random effect where you have to estimate another random factor, another source of variance. And and in many instances, scientists may not always model their effects as random effects when they should. And this is what Tagliarcon is describing in this generalizability crisis paper that I really heavily recommend. I'll put the reference in the slide. And so, so random versus fixed effects. Random consider another source of variance, fixed one source of randomness. And for instance, you have like several observations per groups, many groups, and linear regression where you can actually fit the slope and the intercepts that could vary with groups. So in this paper, like Talia Arconi was showing, for instance, an example of let's say you are interested in the Stroop effect. The Stroop effect is the effect where you are slower to when the discordance of information, non-corresponding information. For instance, if you have the word red written in green letters, you would have like a slower reaction time for detecting the color, for instance. And the Stroop effects in these 20 experiments, for instance, simulated experiments, where we'll have with a fixed effect using a model with fixed effects, when there's only one source of variance, we'll have a small variability. The effect will have a small variability across all those experiments. While when you're looking at the random effects, if you actually model the effect as random, because each subject or groups may not have exactly the same way of the same source of error, then you find that the variability is much higher, of course, and that's unseen or unestimated variability will inflate the false positive or the false positive in the literature. So as a conclusion, it's critical to really understand the statistical framework you're working with. And often that's going to be the null hypothesis testing framework. The results in the literature may be biased due to the number of effects, the Far-Draw effect, the Wiener's curse, the p-hacking, or poor statistical modeling aspects. And knowing those things, hopefully, will help you not to fall into those caveats. Thank you very much for your attention, and thank my lab and many funders and colleagues.